Welcome everyone to the What Happens When channel, where everyday questions are answered. Before we get into it, why don't you hit the subscribe, like, and smash the notification bell? Okay, let's do this. In the vast expanse of our universe, few events capture the raw power and spectacular beauty of a dying star quite like a supernova. These cosmic explosions, nature's grandest farewell performances, represent both the end and beginning of stellar stories that have captivated humanity's imagination for millennia. Today, we'll venture into the heart of these celestial phenomena to understand exactly what unfolds when a massive star meets its explosive finale. Imagine a cosmic dance that's been ongoing for billions of years, a delicate balance between gravity's endless pull and the furious energy of nuclear fusion. This is the life of a star, but like all things in our universe, even stars must face their ultimate destiny. When a star at least 8 times more massive than our Sun exhausts its nuclear fuel, the stage is set for one of the most dramatic events in the cosmos. At its core, a supernova is nature's ultimate demonstration of the conservation of energy. Throughout its life, a star maintains equilibrium through nuclear fusion, converting lighter elements into heavier ones. This process generates the immense pressure needed to counteract gravity's relentless compression. But when iron forms at the star's core, this delicate balance reaches a tipping point. Iron fusion consumes energy rather than releasing it, and this marks the beginning of the end. What happens next occurs in a time frame that seems impossibly brief for such a massive event. The star's core, no longer supported by fusion pressure, collapses under its own gravitational weight. This collapse happens at staggering speeds, around 23% of the speed of light. In less than a second, the core temperature soars to over 100 billion degrees Celsius, triggering a chain of nuclear reactions that would make our most powerful nuclear weapons seem like mere firecrackers in comparison. The collapsing core becomes so dense that even atomic nuclei are crushed together, forming a neutron star. An object so compact that a teaspoon of its material would weigh as much as all the mountains on Earth combined. This collapse creates a rebounding shockwave that, energized by a flood of neutrinos produced in the core, races outward through the star's outer layers. The energy released in this process is truly mind-boggling. In just a few seconds, a supernova can outshine an entire galaxy of hundreds of billions of stars. But supernovae are more than just spectacular light shows. They serve as cosmic factories, creating and dispersing heavy elements throughout the universe. The extreme temperatures and pressures during the explosion forge elements heavier than iron, including gold, silver, and uranium. This process, known as nucleosynthesis, is responsible for creating roughly half of all elements heavier than iron in the universe. Every gold ring, every uranium atom, and many other heavy elements on Earth were once forged in the heart of an exploding star. The impact of these stellar explosions extends far beyond their immediate vicinity. The shockwaves from supernovae compress nearby clouds of gas and dust, potentially triggering the formation of new stars and planetary systems. This cosmic cycle of death and rebirth has been ongoing since the universe's early days, gradually enriching the cosmos with heavy elements essential for life as we know it. Modern astronomical observations have revealed fascinating details about these events. We've learned that there are different types of supernovae, each with its own characteristic features. Type Ia supernovae, for instance, occur in binary star systems, where a white dwarf star accumulates matter from its companion until it reaches a critical mass, triggering a thermonuclear explosion. These explosions are so consistently bright that astronomers use them as standard candles to measure vast cosmic distances. The study of supernovae has also led to groundbreaking discoveries about the universe's expansion. In the late 1990s, observations of distant type Ia supernovae revealed that the universe's expansion is accelerating, leading to the discovery of dark energy, a mysterious force that appears to permeate all of space and works against gravity's attractive pull. When we observe a supernova, we're actually looking back in time. Due to the vast distances involved, the light from these explosions can take millions or even billions of years to reach Earth. This means that many of the supernovae we observe today actually occurred when our planet was young, or even before it existed. This time delay provides astronomers with a unique window into the universe's past, helping us understand how galaxies evolved over cosmic time. The physics governing supernovae represents a fascinating interplay between the known and unknown aspects of our universe. While we understand the basic mechanisms driving these explosions, many details remain mysterious. For instance, the exact process by which the shockwave is energized and propagates through the star is still debated among astrophysicists. Computer simulations have become increasingly sophisticated, but modeling these complex events pushes the boundaries of our most powerful supercomputers. Perhaps most intriguingly, supernovae challenge our understanding of fundamental physics. The extreme conditions during these explosions create environments that cannot be replicated in any laboratory on Earth. This makes them natural laboratories for testing theories about matter, energy, and the fundamental forces of nature. The neutrinos produced during a supernova, for instance, provide valuable insights into these ghostly particles that normally pass through matter without interaction. The chemical elements dispersed by supernovae play a crucial role in the evolution of galaxies. Each explosion enriches the surrounding interstellar medium with heavy elements, gradually changing the chemical composition of future generations of stars and planets. This process of chemical evolution is fundamental to understanding how our own solar system formed and why Earth has the specific elemental composition that made life possible. The diversity of elements created in supernovae is staggering. While stars spend most of their lives fusing hydrogen into helium and subsequently creating elements up to iron, the supernova explosion itself produces elements across much of the periodic table. This includes many radioactive isotopes, which astronomers can detect through their characteristic gamma-ray emissions, providing another tool for studying these events. Recent technological advances have revolutionized our ability to study supernovae. Modern telescopes can detect these explosions in distant galaxies, allowing astronomers to build large catalogs of events and study their properties statistically. Additionally, the development of gravitational wave detectors has opened a new window on these cosmic explosions, potentially allowing us to hear the gravitational ripples from nearby supernovae. The role of supernovae in regulating galactic evolution cannot be overstated. The energy and material they inject into their surroundings can either trigger or suppress star formation, influencing the development of their host galaxies. This regulatory effect demonstrates how individual stellar events can have far-reaching consequences on galactic scales. Looking toward the future, astronomers are particularly interested in stars in our own galaxy that might become supernovae. Betelgeuse, a red supergiant star in the constellation Orion, is one such candidate. While it could explode tomorrow or thousands of years from now, when it does, it will be visible even in daylight from Earth, providing an unprecedented opportunity for detailed study. The pragmatic importance of understanding supernovae extends beyond pure scientific curiosity. These events serve as cosmic laboratories for testing fundamental physics, calibrating our measurements of cosmic distances, and understanding the origin of elements essential to modern technology. Every new observation adds another piece to this cosmic puzzle, helping us better understand our place in the universe. As we continue to study these stellar explosions, we're reminded of the delicate balance between what we know and what remains to be discovered. The physics we've uncovered helps explain much of what we observe, yet new observations consistently reveal unexpected features that challenge our understanding. This tension between the known and unknown drives scientific progress, pushing us to develop better theories and more sensitive instruments. In conclusion, when a star explodes in the sky, it represents far more than just a spectacular astronomical event. It's a fundamental process that has shaped the universe as we know it, creating the elements necessary for life, influencing galactic evolution, and providing tools for understanding cosmic mysteries. These celestial fireworks remind us that in the grand cosmic cycle, endings often mark new beginnings, as the elements forged in these explosions become the building blocks for future stars, planets, and perhaps even life itself. As we continue to observe and study these remarkable events, each new discovery brings us closer to understanding our cosmic heritage while reminding us of the vast mysteries that still await exploration in our universe's depths. Thanks for watching.